Hello, this is May 2018 exam question 4b Markov Chains. This is a gambler's ruin problem where player 1 has an initial capital of k euros and player 2 has the initial capital of a minus k euros, which means the total amount you can win in this game is a euros. In each game, player 1 wins with a probability p. They win €1 and they lose €1 with a probability of q, where p plus q equals 1. That means that they're the only two outcomes from each game. You either win €1 or you lose €1. The game ends when either player's capital is reduced to zero. So if one player loses all their money and ends up with zero, it means that the other player has all the money, €8 as it were. Where Xn denotes the player one's capital, represent the state diagram for this Markov chain process, detail the transition probabilities between states, give the finite transition matrix. 4. Use the state diagram to identify communicating classes for this particular Markov chain and explain why this Markov chain does not have a limiting or a unique stationary distribution. So first of all, we will start with part 1. So we're going to draw a state diagram from player 1's point of view. And remember, each state represents the amount of euros that the player has. So the initial state is state K. This is where they've started, right? At the very beginning of the question on the top row it says player 1 has K euros. That's a starting state. They can win with a probability of P. They will win €1, which brings them up to having K plus 1 euros. When they're at K plus 1 euros, they could lose that when they play the game with a probability Q, and they're back down to K euros. When they're at K euros, if they play the game again and lose with a probability of Q, they end up at K minus 1 euros. When they're at K minus 1 euros and they play the game with a probability of P, they could end up back in K euros. So you can see this pattern now. They increase by 1 with a probability of P, they decrease by 1 with a probability of Q, and that goes the whole way through the chain. Eventually, the player could end up at A minus 2 euros, which is basically €2 short of winning. They could win the next game with a probability of P and end up at A minus 1 euros, i.e. €1 short of winning. But if they lose this game, the next game with a probability of Q, they'll be back down at A minus 2 euros. But consider again, the person is at A minus 1 euros. They're €1 away from winning. They play a game. They win it with a probability of P, and that means they have A euros. They have won the game. They have all the money, and there are no more games to play. So once they have reached the state of A, that's it. They stay in the state of A. Now, I just put in Q for losing, as they can lose, right, over a range, or P for winning over a range, right? There could be an opportunity for the other player to win, player 2 to win, and player 1 could be down at €2. If they're at €2 and they lose with a probability Q, they will end up at €1. If they're at €1, if they've €1 left and they win with a probability of P, they're back up at €2. But if they have only €1 and they lose that game with a probability of Q, they end up with no euros. That means they've lost the game. They're going to stay with no euros with a probability of 1. So that means they are not moving out of that state. Right, so that is the state diagram. You can see there's a fair pattern to it. I've done all the P's in the top row, all the arrows going forward, increasing by 1, and all the Q's underneath as they decrease by 1 because they're losing. Right, so then part 2, detail the transition probabilities between the states. These transition probabilities are given by player 1 wins with a probability of 1, and that's probability is P. Wins €1 with a probability of P, and player 1 loses €1 with a probability of Q. So for I, let I be the state, in which the of euros, how many euros the player has, it's between 0 and A, i.e. it does not include 0 and it does not include A. I includes from 1 up to A minus 1 in the state diagram. So the first situation is they have I euros and then they win. So their I euros are increased to I plus 1 with a probability of P. The other situation is where they have I euros and they lose. So they go down to I minus 1 euros. That's a probability of Q. The other transition probability is that they have no euros. That means they've lost. They're not going to win any more euros. They're going to stay at no euros, and that's with a probability of 1. They've lost all their money. They're ruined. It's the end of the game. Or, on the other hand, player 1 has A euros. That means they've won all the money that's available. They're going to stay in that state of A euros with a probability of 1. They've won all the money, and player 2 has lost all their money, and it's the end of the game. So that's part 1 and part 2 of this done. So part 3 is to define or to give a finite transition matrix. We have to draw the transition matrix. So the transition matrix, P, and then the first row, the first subscript is the row, the second is the column. The row indicates the money that they presently have, and the next after the comma is the money that they will have after one more game. So if you look at P00, that means that they have no money and they're not going to win any more money, and that is correct. When you have no euros, you've totally lost the game and you're going to stay at no euros, and that has a probability of 1. If you go down to the bottom right-hand corner of the matrix, you can see PAA. That means that they have A euros and they'll stay with A euros, and that's what happens. They have all the money, they have won, and they're going to stay at that. So that probability is 1, and you can see in the right-hand matrix that the probability at the bottom right-hand corner is 1. Now, if you go back to the P matrix with all the P10s and you look at the second row down, and that P10 means that the person has €1 and they lose €1 and they end up with no euros. That can happen with a probability Q, and that is why in the same position on the right hand matrix we have the Q. If you look at P11, it's the second over and on the second row, it means P11 means they have €1, they play the game and they have €1 still. That never happens. Once they play the game, they either gain €1 or lose €1, so that's 0. So you can see in that position on the right hand matrix that is 0. And then P12, that is on the second row, but the third over, they have €1, they win the game, and they end up with one more euro, giving them €2. That's a probability of P. And you can only win up to €1. You can't win any more than that, so it's 0 the rest of that row. And this Q0P pattern occurs the whole way down the diagonal of the right-hand matrix. The second last row in the right-hand matrix is when the player has A minus €1. Okay, so if they have A minus €1, they can lose €1 and go to A minus €2. They can't stay at A minus €1. So if they're at A minus €1 and they win a game, they will get up to having A euros with a probability of P. Once they've got that, they'll stay there. So on the bottom row, the 1 is there. Okay, so now the next part of the question is use a state diagram. So there's a state diagram again to identify the communicating classes for this Markov chain. So the communicating classes are where you have arrows going to and from, in between two states. So they will have to be in both directions, from 1 to 2, for example, and then back from 2 to 1, or from k to k plus 1 and back from k plus 1 to k. So the arrows go in both directions. And that happens for all states 1, 2, 3, right up to a minus 1. But it does not happen for state 0, because once you get into state 0, you're stuck in it. That's why it has a probability of 1. That is a closed communicating state. And it does not happen for state A, because once you're in state A, you've won all the money and you stay there, and that is a closed communicating class. So in this question, there are 3 closed communicating classes: 0 on its own, and A on its own, and then all the other classes from 1 up to A minus 1 communicate with each other. That's part 4 done. Part 5, this chain, so we have to find out if it is a unique stationary distribution, but it has 2 closed communicating classes, 0 and A. Therefore, it does not have a unique stationary distribution. And then, does it have a limiting distribution? No, it doesn't, because it's not irreducible. It has more than one communicating class, so it's not irreducible, so it doesn't have a limiting distribution. Thank you. Finished.